Hello, everyone. Thank you. So what I'm going to talk today about is the relationship between different brain networks, predefined brain networks, and the working memory capacity. For that, what we did is we tried to predict the working memory capacity using the resting state functional connectivity within each network. We were also interested in trying to find out if there is any effect of the age on this brain behavior relationship. For that reason, we compared the predictability between these two groups, young and old. One question we can ask, like, why do we want to use predefined networks? We can do whole brain analysis, for example, but it typically results in too many features. With mere 200 nodes, you can end up with like 20,000 features, where the features are many more than the number of subjects. This can lead to challenges for many machine learning algorithms. We might have to do feature selection, and if not done correctly, the accuracy might suffer. Also, the interpretation of the results become difficult. For example, due to multi-collinearity in the data, we don't really know what's driving the predictions. Instead, what we can do is do network-based analysis. So we a priori restrict the number of nodes. That reduces the number of features, and it's a biologically informative feature selection. So if it leads to better predictions, we can say the results are interpretable. That basically means we can directly say a particular biologically meaningful network is predicting a working memory capacity. So to summarize this in short, the network-based analysis can make the machines happy, and we have shown this with two recent papers from our group, and this is the approach that we followed here as well. So what we did, we took 6 meta-analytic networks, in this case, that are shown on the slides. The top 3 were included because they are all related to executive functions, so we suspected that they might predict a working memory. The bottom 3, we were not sure. They're not completely agnostic to working memory, so there were more exploratory reasons why we included them in this analysis. The data came from 46 young and 45 old subjects. All of them completed 4 computer-based working memory tests, and these tests were aggregated at the individual level to create a composite score. So I will refer to this score as simply as a memory score for now, for simplicity. So you can see on the graph that the age has an effect. So basically, the scores for the older subjects are much lower, statistically lower than the young subject. This is not unexpected. But we also tested for variance, and the variance between these two groups did not differ significantly. We also, of course, collected the resting state fMRI data for these subjects. For the analysis, what we did, we calculated the within network resting state connectivity for each of the subjects, and then used the machine learning approach. Our aim was to find generalizable predictions. So what we did is a 10-fold cross-validation for each network, and then repeated this cross-validation procedure 250 times. The reasons for this will become clear very soon. We also used the relevance vector machine as our approach for regression. The reason we use this because it typically leads to very sparse models, so which can help us to interpret what's exactly driving the predictions. The analysis was done in 3 groups: the all group, which combined young and old, and of course in young and old groups separately. So here is an example analysis pipeline. So we start with the nodes. For each node, we extract a representative time series, and with this time series, we can calculate all pairwise connections for each subject separately. For illustrative purpose, what you see on the right-hand side is the average resting state connectivity across all the subjects, right? So some connections are stronger and others not so much. But in our approach, what we do is basically we vectorize the connections for each subject, represented as a row in our matrix, and this can be the input to machine learning algorithm together with the memory score that we have. So we are trying to predict the memory score using the connectivity profiles for each subject. So as I said before, we do a cross-validation analysis using RVM, and then we repeat this 250 times. And if this is deemed significant, we can ask the question, which connections are very often used? So remember, RVM is a sparse method, so we can say something like, hey, how many connections are used most frequently? For example, 90% of the time, and then we can threshold this map, and I will show you some results that come out of this afterwards. I'm going to show you results in terms of more summarized format than the scatter plots. So they're represented as a bar. So this is the bar graph is the average across all 250 replications, and the error bars basically show the variance that is captured by these replications. Because the analysis was repeated in 3 different groups, so we have 3 bar graphs for each network. So in this case, the working memory network, the gray is the all, blue is the young, and the orange is the old. So we repeated this for 6 networks, if you remember. The interesting result is we can actually predict working memory capacity using predefined brand networks. We use a Pearson correlation to define what is predictive or not, so our measure of accuracy. Interesting result is, except one network, in 5 of the 6 networks, the older subjects are much more predictive than the younger subjects. And also important to note is like 5 networks predict the working memory capacity in the older subjects. Here are some example predictions. So what happens is, as you can see, there are differences in the networks. For example, the first working memory network shows predictability in the all and the old subjects. The emotion regulation network shows predictability only in the young subjects, while the theory of mind networks predictability only in the old subjects. As you can notice, there is error bars around all the points, and that's because of the repetition of the cross-validation procedure. Because we repeat it multiple times, it's important to capture this variance, because if you do it only once or twice, you might hit the low or high ends of this. There might be some sample effects as well. So it's important to do this procedure again, sorry. Again, to reiterate, RVM induces sparse weights. So we basically ask the question, okay, which of these connections in the old group, so the results are only for the old group, appear in at least 90% of the times in all 2,500 models that we built. So 2,500 comes from 250 times repeated tenfold cross-validation. What we see here is basically most of the interhemispheric connections stand out. So it will be interesting to see why this reason is. So these are preliminary results that we have here. And these are very sparse graphs. So it will be interesting to see which other connections show out. Okay. So in conclusion, one of the important things to notice is we can actually predict the working memory capacity using resting state networks that are predefined. So we are not doing the whole brain analysis, but therefore we can actually see some of the networks are predictive of this working memory capacity. The predictability was much more higher in the older subjects than in the younger subjects. So why this happens is we speculate that the composite score that we calculated by combining 4 different scores captures some common factor of working memory, which is associated with age. So therefore, it's more predictive in the older subjects and not so predictive in the young subjects. Also, we saw that the 5 networks out of 6 are predictive in the old subjects. So we again think that there are 2 possible reasons for this. One is the differentiation of the networks, so the networks themselves becoming more similar, and therefore they predict the working memory. Or equivalently, it's also possible that there is a compensation. So there are multiple networks that are being recruited to do the similar task. So both of these processes can lead that multiple networks predict the working memory capacity. We also said there is quite some variance in the predictions, so it's important to repeat the cross-validation procedure to capture this variance. Finally, to acknowledge, I would like to thank all the group, especially Raquel, who did quite a lot of this work, and also our funding agencies. So if you're interested, please come by to our poster 2301, and I would be happy to discuss any more details of this. Thank you.